and in today's lecture we will discuss the generic example of asymptotic notations first, and then in the second phase of this lecture we will discuss the programming examples with respect to asymptotic notations. So let's start. Now here you can see that we have two lists of fruits. In the first list is alphabetically sorted list, and we have a list of n items, which means we have a list of n number of fruits in the first list, which is alphabetically sorted list, right? So in first list you can see that all the apples are in sorted order. You can see that B for banana, B comes just after A, G comes after B, O comes after G, and comes after O. So the first list is in sorted order. And here we have a unsorted list, which is a random list, and all the items or all the elements or all the fruits are inserted in a random order. So it's a unsorted list. So suppose, talking about the asymptotic notations, let's take an example. Suppose I want to find banana in an alphabetically sorted list. So because the list is in sorted order, so I can quickly find it, and it will take a constant number of operations for searching or finding banana in alphabetically sorted list, right? You can see that suppose we want to search or find banana in alphabetically sorted list, so we can quickly search it because the list is an alphabetically sorted list. So it will take constant number of operations and a lower bound. So the complexity of searching banana in alphabetically sorted list is omega 1 or O1, right? Let's take another example or another case. Now here is case number 2. Now suppose we want to search banana in alphabetically sorted list and we have hundreds or thousands of elements starts with B. What does that mean? Suppose we want to find banana in this list and we have hundreds or thousands of elements. We never know how many elements. We have hundreds or thousands of elements starts with B in alphabetically sorted list. So obviously it won't take constant number of operations. The list will be further break into the list will further break. So it will take constant number, it won't take constant number of operations. It will take logarithmic time. Whenever the list is breakable, whenever we have subtypes, whenever we have subcategories, whenever we have a list in the form of tree, so we will call it a logarithmic time. So the complexity of finding banana in a list would be O log n. Let's read it again. Suppose we want to search banana in alphabetically sorted list and we have hundreds or thousands of elements starts with B, so we will further break that list and it will take logarithmic time. So the complexity of searching banana is O log n, right? Whenever we break that list, so we will call it log time. We will call it O log n. So the time complexity of finding banana whenever we have hundreds or thousands of elements starts with B would be O log n, right? Let's take another example. Now suppose we want to search banana in an unsorted list or random list. So we will have to go through the whole list because the list is not sorted. So the time complexity of searching banana is O n, which is a upper bound. Now see that list. If I ask you to find banana in a random list, so we have to search or find the whole list because the list is not in a sorted order. So time complexity of finding banana in a random list would be O(n), right? I have written all this what I have explained you, so you whenever you see that video you can understand it in a more convenient way, right? So if I write the conclusion of the above three cases, we came to a conclusion: alphabetically sorted list is randomly faster than an unsorted list. So as far as time complexity is concerned, omega 1 has less growth than O log n, and O log n has less growth than On, right? So we can say that omega 1 has less growth than O log n, and O log n has less growth than On. And O omega 1 is a lower bound. As far as growth is concerned, lower bound has a less growth than tight bound, and tight bound will have a less growth than upper bound. We can either say that lower bound has more efficiency than the tight bound, and the tight bound has more efficiency than the upper bound. So growth is equal to 1 upon efficiency, which means whenever whenever the data have a less growth, it means it will have a high efficiency, and whenever the data will have a high growth, which means it will have a less efficiency, right? Let's discuss some programming examples with respect to asymptotic notations. Now we will discuss the programming examples with respect to the following topics. First of all, we will discuss constants, then loops, then nested loops, then sequential, conditional, and logarithm. So let's discuss it one by one. First of all, the constant. Now, in this example, I have discussed I have written a simple function. The first void means no pass any value. Here is the function. It could be any function, and I am passing an argument of type integer, which is n. I am passing n argument of type integer, right? So in the given code, I have initialized I is equal to 0, and the loop I have initialized a loop I is equal to 0, I less than 10 and I plus plus, so which means this loop will run to 10 number of times from 0 to 9. So here is a simple code. Now the point is, you can see that in comments whether I is less than 10 or I is less than 100 or I is less than 1000, etc., etc. We consider it as a constant and the time complexity is On. I repeat, it doesn't matter how much bigger the value of I is. Whenever we have the value of I in the form of constant, constant could be 10, 100, 1000, lakhs, 10 lakh, crore, etc., etc. Whenever we have the specific number of iterations, so it will take constant number of time and the time complexity would be O1 or omega 1, right? Let's move on. Here we have a loop. In the above code, I have initialized a for loop with 0 and the iteration would be n. You can see that it will take n number of iterations and I have used a simple increment operator. Now loop will run. I've used comments in every code for your convenience. So when you read the comments, you get to know the function of the loop. So in the given code, the loop will run n number of times. So the complexity of the above code is On, right? Let's take another example of a loop. Here you can say that, here you can see that this loop will also run n number of times, right? And just after the loop, I have used a break statement. What does that mean? The loop will run n number of times, but because of break statement, loop will execute only once. So time complexity is On. The loop will run n number of times. So obviously the time complexity of this loop would be On. But because of break statement, the loop will run only once. So the time complexity would be O1. Right? Let's move on to nested loop. Here you can see that nested loop. Nested loop means whenever we have a loop inside another loop, we call it a nested loop. Right? So here you can see that we have two loops. I've initialized I is equal to 0. I've initialized j is equal to 0. The first loop will run n number of times and the second loop will also run n number of times. The time complexity of the first loop would be On and the time complexity of the second loop would also be On. Now the rule is whenever we have two loops in the same body, so we just multiply the complexity of both loops. So according to rule, when we have a nested loop in same body, so we multiply the complexity of both loops. So the overall time complexity of above loop is On square. Right? Let's take another example of nested loops. Again, the loop will run n number of times. So the time complexity would be On. And this loop will also run n number of times. But because I have used a break statement just after the second loop, so the first loop will run n number of times and the second loop will run only once because of the break statement. So according to rule, whenever we have nested loop in same body, so we multiply the complexity of both loops, so the overall time complexity of the above loop would be On multiply O1, so the overall time complexity would be On, right? Let's move on. Sequential. So students, I hope you people must have studied what is sequential data in data structure. Let me remind you people, what is sequential data? Sequential data is a form of data The example of sequential data would be text streams, audio clips, video clips, time series data, etc., etc. Right? So here is an example code of a sequential data. Here I have initialized three variables: I is equal to 0, j is equal to 0, k is equal to 0. Right? In the first body, I have used three loops. You can see that the first loop will run n number of times. The second loop will also run n number of times, so the complexity would be On, and the third loop will also run n number of times. So the rule is just like the previous example, whenever we have the loops in the same body, so we just multiply the complexity. So whenever we multiply the complexity On multiply On multiply On, so it will become On cube, right? Here is the second body. We have two loops in this body. The first loop will run n number of times, so the time complexity would be On. The second loop will also run n number of times, so the time complexity would be On. So whenever we multiply the complexity, we will get On square. In the third body, the loop will again run to the n number of times and the time complexity of the above loop is On. Because it's an example of sequential, so the rule is quite simple. Whenever we have loops in the same body, so we just multiply the complexity, and whenever we have different bodies, so we just add the complexities. So according to rule, we just add the complexity of different bodies. The complexity of first body would be On cube. The complexity of second body would be On square. The complexity of third body would be On. So it will become n cube plus n square plus n. For your convenience, I have written all the explanation in note. So when we have loops in different body, we add the complexity. So by adding, we have get n square plus n square plus n. So by considering the highest power, worst case, the overall complexity is On cube. Why should we take On cube, we have discussed this point in lecture number 2. Whenever we have complexity in the form of expression, we only care about the highest power. Why we care about the highest power? Because highest power represents the whole array. Highest power represents the worst case. And whenever we analyze the complexity of algorithm, the complexity of data, the complexity of array, we are always interested in the worst case. That is why we only consider the highest power and ignore the rest. So the overall time complexity of the given code is O n cube. I hope you have understood. Let's move on. Now, here is a conditional statement. In the above code, I have taken three variables, I is equal to 0, j is equal to 0 and k is equal to 0. If I am passing an argument having identifier n of type integer, if n is greater than 20, so this body will execute. I have used three variables in this body. The first loop will run n number of times and the complexity would be On. The second loop will also run n number of times, so the complexity would be On. The third loop will also run n number of times, so the complexity would be On. So whenever we multiply the complexity of three loops, it will become On cube, right? Now, if n is greater than 20, so this body will execute. Else if n is greater or equal to 10, it's a relational operator. It's a logical operator and it is also a relational operator. So else if n is greater or equal to 10 and n is less or equal to 15, so this body will execute. The complexity of the above loop is On. The complexity of the second loop is also On. So according to rule, whenever we multiply the complexity, it will become On square. Else if n is less than 10, so this body will execute and the complexity of the given loop, because the loop will run n number of times, would be On. Now the noticeable thing is that in this specific code, we won't add up the complexities just like the sequential, because in this specific code only one condition will be executed at a time. Why? It never happens a student can have A plus grade or A grade or B grade or C grade, etc., etc. A student can have only A plus or A or B or C. It never happens. It is not possible for a student to have all the grades at a time, right? So whether this condition will execute or this condition will execute or this condition will execute, right? So if I write the analysis, I can write it. In the above example of code, the time complexity would be, best case time complexity would be On, average case would be On square, and the worst case would be On cube. So best case would be On, average case would be On square, and worst case would be On cube. I can even say that lower bound is On, tight bound is On square, and the upper bound is On cube. So as far as growth is concerned, lower bound has less growth than tight bound, lower bound has less growth than tide bound, and tide bound has less growth than upper bound. I can even say that lower bound has high efficiency than tide bound, and tide bound has high efficiency than upper bound, because we know it very well, growth is inversely proportional to the efficiency. Got it? I hope you have understood. Let's move on. Here is a small uh, code of logarithm. Now you can see that I have initialized I is equal to 1. While I less than n, it will run till kth iterations. So time complexity would be O log 2n. Why O log 2n? We know it very well. Whenever we have a data in the form of a tree, or whenever we break that data, whenever we categorize that data, whenever we break data in several types, so we use log. So here I is equal to I multiplied by 2. Whenever we find the value of I, we will further multiply it by 2, right? So students, whenever the value of I will come from the loop, the value of I will be multiplied by 2. For example, 1 will come, so it will multiply by 2, it will become 2. 2 will come, it will multiply by 2, it will become 4. 3 will come, it will multiply by 3, it will become 6. And this process will go on till the kth iterations, right? So the complexity of such kind of a loop would be O log 2n. So students, I have tried to explain you people the asymptotic complexity from the basic programming examples. I hope people have understood. In the future classes, I will try to explain you people the programming examples with the help of SFC table. So at the end of this topic, I conclude lecture number 3.